Okay, so hey Cedric, can you see the slides?
I think you haven't shared them.
Can you see them now?
Okay, that's fine.
Cool. So hi everyone. Today's recitation is to discuss about the classification and verification parts for homework 2 part 2. And I'm Aditya, and we also have Cedric today from Kigali, and we're going to be our lecturers for today. So let's get into it. So this is our agenda for today, and the main goal of the recitation is to acquaint you with the problem statement for homework 2. And we're going to talk about how to formulate the phase classification and verification tasks, and discuss a bit about how the task and the data is different from past semesters. And then we'll talk about a few approaches to verification, and then Cedric will go into the different types of convolution layers that you will encounter as you implement the architectures that we discussed in the bootcamp yesterday. So a quick note, there was a bootcamp yesterday. Please refer to it for model architectures and other specific ideas about what to implement for part 2. And finally, we will run through the start notebook for homework 2 part 2. Great. So if you've read the write-up, then by now you know that we have two tasks for homework 2 part 2. And one is phase classification, which is pretty straightforward. Given an image, figure out which person it is. So it's from a limited set, so there are a finite number of options. And the other one is phase verification, which is determine if the person given in a query picture is also present in a given gallery of images or not, with no reference to their identity. And if that sounds complicated, then hold on for 15 minutes and we'll get some more clarity about what that means. And yeah, feel free to ask any questions at any point in time. So in general, classification is an n-way like segregation task. You should predict from a fixed set of possible output classes. And so at test time, when you get an image, you just have to assign it a label from a predefined space of classes. Verification, on the other hand, is a matching operation where you match a given sample to, say, the closest sample from a reference of n other samples. So this can be also looked at as like a one-to-one task where we want to verify if two embeddings are similar or like whether they belong to the same class. But it can also be extrapolated to like you have one image and you have n other images that you want to compare and find out which ones are similar or belong to the same class. And of course, you have to define how you measure closeness here. It can, so yeah, I mean the general idea is that you like try to look at phase two embeddings and try to tell whether they belong to the same category or not. So over here, it's useful to talk about open set versus closed set. So a closed set classification task would be that at test time, you're guaranteed to have a category that you have seen before. And whereas in an open set task, you have classes or identities that did not appear during training time at all at test time. So at test time, your model is shown an image from a category that it has never seen before. So just going off of that information, I'd like to just ask you all, what do you think is the mapping here? Like, is classification open set or closed set, and what do you think about verification? Yeah, feel free to unmute yourself and just say or type in the chat or whatever. Anyone? Okay, it's not that hard. Like we just talked about, right? Where in classification we have a fixed set of classes. So classification is the closed set and verification is open set. So this is just a bit of formulation about how it works. Right. So classification, you have identities that appear in the training set. At test time, you're going to have to compare them and assign them, not compare them, sorry, at test time, you just have to assign them a class. And whereas in open set, face recognition, which is face verification, is a part of that class of problems. You are given an identity, and at test time, you will have to compare it. You may not have seen that identity, and you'll have to compare it with other identities and assign it a class based on that. Okay. So yeah, we just talked about it. Classification is closed set, verification open set. So let's talk about training. What task do we have at hand? How does that impact how we train our models? So the general training pipeline for classification tasks will look like this. Like we're given an image, we'll use some convolutional architecture as a feature extractor to get some feature embeddings. You can also call them face embeddings. And again, to know more about different kind of architectures, please go back to yesterday's bootcamp. And the CNN will extract embeddings from the feature, and then you'll have a linear layer, also called as a projection layer sometimes, that will project the embeddings onto the categories or the identities in this case. And for training our classification task, we'll use our favorite cross entropy loss function and the standard loss function for any sort of multi-class classification task. And for regularization, we can do things like label smoothing and even weight decay to prevent overfitting. We'll talk more about that later. So nice. Our cross entropy loss does its job, and the features are separable. And our loss is like, if all the features are perfectly separate, loss is 0, and we've achieved nice classification. So first question I would like to ask is that how can we use this network for verification? Does anyone have any ideas?
If they're already if their face if the face of the person we're testing is in the classifier, then we could just search all the pictures for the same name as the test image.
Yeah, so you're saying that then we would compare closeness with all of the classes, with examples from all the classes. So like for verification, you'll be given 2 images, and you have to tell whether they belong to the same class or not. In that case, like what would you do?
Throw both in the classifier and see if they output the same result or not. If they put the same result, then they're probably the same person.
Okay, but they're not present in the classes that your classifier is trained on. Does that make sense?
Yeah.
Yeah. So you'd do like something like what we talked about in this case. You'd get the embeddings, and you would compare the similarity or some distance metric between those embeddings, and you'd sort of define a threshold that, okay, if their cosine similarity is close to 1, then I'll say that they belong to the same class. And if it's like lesser than say 0.5, then I'll say they don't. So that's how you would go about it. You have to define some distance metric, some idea of closeness, and you can use the same network for verification. But the next question is, are the sort of embeddings that we would get from training for a classification task good enough for verification? Sure, we would get like, linearly separable embeddings, but is that also good enough for verification? Any idea about that? Any thoughts on that, really?
Not necessarily. Our linear layers can learn an arbitrary decision boundary. It doesn't really guarantee us that the intra-class distance is smaller than the inter-class distance, which is what we really want for verification.
Yeah, exactly. That's completely on point. And like, like even even if it is linearly separable for known classes, we won't even know what it'll do for unknown classes because we're just training it on that space. So right, no, it's not good enough for verification, and that like again to think about that, we just have to think about what the task for verification is, and we essentially want to determine if a person in a query image is also present in a gallery of images or not, with no reference to their identity or class. And what's the requirement for that to be able to happen? As I think Peter or someone just pointed out, we will require that the embeddings of two pictures of the same person are always closer than those from pictures of two different people, and which we can see is clearly not the case here, which can cause a lot of confusion to our model. Okay, so ideally, we want something like what we've shown on the right. We want to maximize the interclass distance. Oops, sorry. Yeah, we want to maximize the interclass distance, and we want to minimize the intra-class distance. Yeah, I'm just going to try to annotate this here. So yeah, we want to maximize this distance, and we want to minimize the intra-class distance. So essentially, we want to sort of maximize the margin between these two classes. And yeah, we want the embeddings of two pictures of the same person to be always closer than those from two different people. Okay, so how can we do that? How can we we just talked about training our model for classification, but how, and we saw what kind of embeddings that would give us, but we now have an idea of what we want. How can we get those kind of embeddings? How can we get more discriminative features? Any ideas about that?
We have to sort of change the way we train, and instead of just training the classification task to get the embeddings, we need to explicitly try and get embeddings that are discriminative. And so with the find loss function, that captures what it means to be discriminative.
Yep, that is exactly right. And in other words, we want to use a loss function that strongly correlates to our task or evaluation criteria. And this is a important idea in deep learning, and this is something you will encounter again in the next homework and in the next week's lectures as well, I think. So our cross entropy was a good choice of a loss function when we were evaluating a multi-class matrix. But for verification, where we have this added requirement of discriminative features, we need something more tailored to this problem. And yeah, enter contrastive losses. So
can I ask a quick question about that?
Yeah, go for it.
So I feel like I can imagine that loss function where instead of a single training instance, you pass in maybe two training instances, and the loss function should be 0 when they're the same. You know, when you know they're the same, and it should be infinite when they're not the same or whatever. But just speaking practically, like I'm not sure how to like the data loaders that we're working with, they go through in batches, right? And so I feel like they're feeding in things one by one. I don't really know how to feed it in pairs. If we're going to talk about that later, that's great. But I would just love a little bit of context on how to think about
so that's a good question. I would tell you to go back to yesterday's bootcamp. You're exactly right.
I haven't had a chance to watch that yet, so I will watch that.
Okay. No, but this is like a good question. Like that, I don't think it was asked yesterday, but yes, you will need to create your own data loader because your standard data loader will just give you one class, and you will have to do some way to mine for pairs. Like, so like, okay, just like I'm going to refer you to the bootcamp for losses, but we're going to go through a quick example here. If that clears it out, then that's good. Otherwise, you can come by later. Okay. So yeah, just we talked about, we need a contrastive loss. So we want to use a contrastive learning-based training objective whose general aim is to do what we discussed above, like maximize the interclass distance. If two images belong to the same category, we want to minimize the distance between them. And we want minimum interclass distance. If they belong to the same category, we want to minimize distance and maximize interclass distance. If they belong to different classes, we want to maximize the distance between them. And again, by distance, it could be multiple things. It could be Euclidean distance or a similarity metric like cosine similarity. So one such loss that would be intuitive here and kind of similar to what I think Eric was alluding to, but not exactly, is triplet loss. And yes, contrastive losses were discussed in detail in the bootcamp yesterday, which you should refer to for that, for triplet loss and even other kinds of losses. But we can quickly see the idea behind triplet loss here. So the idea is that we have an anchor image while training, and we also pick a positive sample and a negative sample. So the positive sample belongs to the same category as the anchor image, and the negative sample does not. And we define a loss that minimizes the distance between the anchor and the positive sample and maximizes the distance between the anchor and the negative sample. And that can be modeled by this equation here. Again, I would like to say, like Eric pointed out, it's not plug and play. There are definitely implementations of triplet loss that you can play around with, but you will have to mine for challenging positive and negative samples. You can't just pick any. That's not very useful to the model. So you want to pick examples like this one, the one that we just showed here, because you can see here that the distance between the anchor and the negative example is less, and we want to increase that. And the distance between the anchor and the positive is high, and we want to decrease that. So this is a good training example, and you would want to mine for these kind of training examples, which is not like just plug and play or trivial. Right. Does that help answer your question, Eric? What was that, Eric?
I think it sounds like we'll have to write a data loader to do this.
Yeah, exactly. You will. Yeah. We'll help you out with that. So don't worry. These are other losses that were covered in the bootcamp, and sphere face is actually proposed by Professor Diksha, so you can ask him about it. But please check out the bootcamp for some tips about which ones we found to work best on our data set. See the discussion. So now let's move on to our data set. Hold on. Before that, just like what do you I just want to discuss, what do you think could be a use case of face verification? We have classification, which we had a lot of discussion about, but why and when can face verification be important in the real world? Any ideas or any thoughts about this?
I don't know, security entrance into a building.
Yeah, sure. That's a good one. Biometrics, right? To verify the identity. Anyone else?
Airports will pay billions of dollars for that technology.
Right. But for some reason, I don't see how scalable that will be. Yeah, but I'm sure it'll happen. You're right.
If it was highly accurate, very effective.
Yeah.
That's the trick.
Yeah, exactly. Yeah, I agree. But one place where it is used right now is so imagine you're the police and you're given a photo of a criminal and you want to locate them. So in that case, the criminal probably doesn't exist as a class in your face recognition model. Like if it does, it's probably not a very good criminal. So you have to scan for them through all your surveillance cameras and like get your images, pass it through your CNNs, compare the face embeddings and match them with your surveillance feed. And this is like a verification task. But also it's like, so when you look at it on a higher level, like since you have to retrieve the person given like n images, it's also like an image retrieval problem. And in the real world, the person that we're looking for may or may not even be present in the database, or there may be like multiple query images, in which case like the retrieval gets more complicated as you'll have to use like some top K metrics, but that's not in the context of this homework. I just want to discuss it. So let's talk about what is. So we're just gonna briefly go over the data set. The data set that we'll be working within this homework is the state-of-the-art VGG phase 2 data set. I think like, as of 2020, it was the largest compilation of face like data set for machine learning in the world. I don't know if that's true now, but yeah, it has 3.3 million face images, around 362 samples per subject, 9,130 identities in total with good variations. And for our tasks, we will have 7,000 identities for the classification task and 1,000 other identities that we're not going to use to train our model for classification. And we also know some demographics of the data, like age and ethnicity. And yeah, this is a state-of-the-art data set. So like you like once you get your good results on this data set, you can definitely like brag about it. So yeah. So yeah, I want to talk a little bit about what we're changing this semester. Classification remains the same. It's the same test and training data set with 7,000 identities, but we have changed the verification task this semester from what it usually was in the previous semesters. And before we talk about what it is now, let's see what it was. So for verification, like previously, even when I took the course, we were given 1,000 pairs of images with labels about whether they belong to the same person or not. So like just, the positive and negative pairs, like if two images belong to the same person, it's a 1. If they don't, it's 0. And the positive and negative pairs were sampled randomly from the test set of VGG phase 2. So to quantify how good our network was at this task, we were supposed to report the AUC. It was just the probability of our network rating a random positive example higher than a negative one. So as you know by now, the idea behind verification tasks is to, like, as you would have guessed by now, like we have verification to have the students learn to implement and explore contrastive losses. But for this problem, the classification network itself gave a pretty good performance on verification as well. And students were able to get their way around it without having to use metric learning. So can anyone think of a possible reason why this may have happened? Like, why did we not need to use contrastive losses to improve our verification accuracies? Any idea? I did drop a hint there.
The people were in the training set. The people for the verification that was in the training set, maybe.
No, it wasn't that. No, they were unseen people. Okay, so one of the reasons that we think it could be was imbalance in the demographics, which makes the task of distinguishing identities much easier. So like think about it, like distinguishing between people of different ages and like different ethnicities is harder than distinguishing between people from the same demographics. So since they were sampled at random, that bias may have crept in. And another thing that is to be noted here is that pair matching is much easier than the gallery formulation that we talked about. because like you have more options and there's more room for confusion. Right. So here's what the verification task is now. We have in the test set, we have a balanced set of 1,000 known identities, and we have 1,000 unknown identities. So the task is to find the similarity between each unknown identity and all the known identities, and then predict the one with the highest similarity. So for each known identity, you will assign like whichever has the highest similarity with it, assign that unknown identity to it. And it's kind of, so you have to come up with a one-to-one mapping. And what we mean by balanced here is that we have the demographic information about age and ethnicity, and those are equally represented in the identities in the test set. And yeah, I think from our experiments, we have made this, we have achieved our objective and made this task harder.
You said it's one-to-one?
Yeah.
Okay.
Yeah, or for more description on this, like you can read the write-up. I think we've described it in pretty a lot of detail over there. Cool. So now Cedric will talk about the different types of convolutions. Cedric, do you want me to stop sharing?
Yeah. Can you see my screen?
Yep.
Okay, right. So we're gonna have a short discussion about the types of convolutions. So basically we would just like give you more reason as to why using depth-wise convolution is way better than using the conventional convolution layer. So the idea is, so as we've discussed in class, like using the conventional convolution, what you do is you have a kernel which has the same dimension as the input image. So let's say here you have like a RGB image. So basically you would just have a filter with the same like 3 dimensions, and then like you perform your convolution using that kernel. So ideally what you will have is you have an input channels, so you require and filters, and those filters will be used to perform your convolution operation, and then you also have like a mapping operation at the end to kind of generate the output maps. So the challenges with this operation is basically the number of parameters that are required for you to perform convolution. So like we said, using this 2D input image, you actually have like this total number of parameters that are required for you to get your convolution results. So for the very low cutoff, you don't even need to kind of like, think of depth-wise convolution. You can still use the conventional one. But like this is basically for those who are gonna start working on how they can achieve a pretty high score for classification as well as verification. So talking about depth-wise convolution, you actually perform convolution using 2 stages. So the first stage is actually what we call like you apply your usual convolution. The only difference is you're using actually like a different set of filters. So for any given channel in the input image, you actually use one filter of size K by K. So this is just like divided into 2 different operations. So the first one is actually your convolution operation. And the second one, which is also a convolution operation, is usually referred to as a combination. So this is actually using a 1-by-1 by the number of filters that you have to perform your convolution. So the first stage, like we said, is actually the filtering part. So we have to use, you set a kernel size, which is K. So for a 2D image, you actually have a K by K filter. So for any given channel, you actually use one single filter or one single kernel for this particular image channel actually. And after you perform this operation, then you have to kind of generate this output map, and this is actually done using a 1 by 1 by m, which is like the number of channels that you have. And using this operation, you actually have less operation to perform. So let's go into this quick example. So we actually have this 8 by 8 input image with 3 channels. So if we actually start with specifying the number of filters that we actually need, so we desire 256 filters with a kernel size of 5. If you use your conventional convolution, you actually require this type of kernel actually. So a 5 by 5 by 3, which is the number of channels. And since you want to kind of have 256 such filters, you actually need to perform this multiplication across all the dimensions, and it will actually end up having this total number of parameters for you to perform your convolution. However, if you use depthwise convolution, what you actually have is first stage, which is the filtering part. We actually have 3 different filters, 1 for each channel. So the same size is actually k by 1. So this is actually fewer parameters that you're gonna use for the first stage. And the second stage would be the combination stage, where you actually use these 1 by 1 times the number of dimension that you have in your input channel. So basically, this is the number of parameters that you will actually have after performing this combination stage. And the total number of parameters is actually this one. So you basically have something like 23 fewer parameters for this depthwise convolution. So I guess like you actually have an idea of what you desire for your network actually, since for this work, for both classification and verification, you actually have this standard size, which is 224. So if you actually want your model to run faster, you basically need a faster convolution layer. And I think yesterday we actually discussed such architectures, namely MobileNet, ConvNext, that actually use those convolution layers. So we actually have now a discussion around how you design your networks for both classification and verification. So the first
quick question.
Yeah, yeah, you have a question.
Is depthwise convolution available in PyTorch, or do you have to build it up with 2 conv2d layers?
So you have to actually build this layer on your own. Actually, there is, like, you can still use the same, like, nn.conv2d class to build it. The only difference will be for you to perform depthwise convolution, you need to kind of set this group's attributes to the desired number.
Okay, so you stack 2 of them on top of each other.
It's actually the same layer, so it depends, because if you, let's say if you actually want to go with architectures such as MobileNet or ConvNext, so you have the depthwise convolution, which is basically the regular convolution with, okay, let me just go back to the slides. So with this parameter, like groups, set to the desired number, so we have to figure this out. And when you have this one, usually you have like you have to build a stage. So a stage will be one conv layer, normalization, and some other layers such as activation and so on.
Yeah.
Go ahead.
Sorry, what is groups? That one I'm not familiar with.
Sorry?
The groups argument? I don't think I've ever used that one.
Yeah, so usually like the default value is 1. So when you define your convNext, like your conv2d layer, you don't even have to pick this parameter, like since you don't even need like a depth-wise convolution like as default. But when you want this behavior of like reducing the number of parameters, but actually having a faster convolution operation, you need to set groups parameter to the number of output channel, or actually the number of desired output channel that you want for you to actually perform this operation instead of the conventional convolution.
Okay, so when you set the groups variable, it means you can do a depth-wise convolution in a single call?
Yep.
Okay, thanks.
Pleasure. So, yeah, go ahead.
Another quick question. So would you be able to share any intuition on why lower parameters, lesser number of parameters with depth-wise convolution still works better than the conventional convolution with more parameters?
So the thing is, like, they don't work better, they work faster. Because like you actually have the same convolution operation. The only thing is like, yeah, given this number, actually, like you have for the original convolution is how much parameters that, like how many parameters that you need to kind of like, perform this operation. And using depth-wise convolution, this is actually the number of parameters that are required for your network. Okay.
So in terms of performance, is the same.
Yeah, but this one is faster than the conventional one.
Got it. Thanks.
So let's go ahead and have a discussion about the setup for classification and verification. So you have the choice of the approach that you want to use for both classification and verification. So the first one is actually having a joint loss that you have to optimize for you to get your verification model while you're training your classification model. So in this setup, you actually have the same convolution model that is what we call model here. And depending on the setup, so let's say you want to perform something like triplet loss. You also need a data set of triplets. So namely, when you call this data loader for the triplet data set, you need an anchor image, you need a positive image and a negative image. So then through your model, you actually generate the embeddings, which are basically the output of the penultimate layer of your network. And using your labels, you compute your regular cross-entropy loss. So that will be the first step for this particular approach. Second one would be, since you also want to train a verification model alongside this model, you also need like those embeddings, given that in this example, we'll consider that we're using triplet loss for the verification task. So as you complete those embeddings, you also need a contrastive loss. So triplet loss will also be used in this case. And you then have like two different losses. So you need to combine them into one loss using, like you can even go with like a weighted sum. And then you basically have to optimize this weighted loss actually. So this is actually how you will design your training approach to account for these two losses. So ideally, you kind of get your losses from your model using the regular classification model. And then using the same model, since you also want to perform verification using the same model, you can actually get the features from your model for any given image that you consider. So in this case, we're using triplet loss, so we have like 3 different images. Then given those embeddings, what you do is you compute your different losses, and then the final loss will be a weighted sum of those 2 losses. So feel free to ask if you have any question about this particular step. But this is how you actually build your training pipeline for the joint loss optimization. The second approach will be a sequential one. Okay, I see one and I go. Okay, you have a question?
Yeah. For the old one, why is it that we need to do a positive and a negative one at the same time? Why can't we just like say, instead of doing a triplet loss, just do random pairs, and then if it's positive, then it's positive. If it's negative, then it's negative. Like, what goes wrong? Why do you need triplet?
So like you actually want to know why we use this approach, like this joint loss optimization?
I mean, why do we need to use why do we need 3 instead of like say 2, where we used to do a pair of 2 random photos?
Yeah. So the thing is, like in the regular setup for triplet loss, you actually need 2 things. So you need like a positive image and a negative image. So the thing will be, you actually compare your those 2 embeddings to the normal anchor image that you have. So you actually need 3 images, and those 3 images, like you actually need to reduce, like we explained, like actually we also explained it like in the bootcamp. But what you want to achieve using this loss is you want to reduce the intra-class distance, and you also want to increase in-class distance. So that is actually, you want to have your negative pretty far from after you train your model, you kind of have a distance between your negative embeddings and the anchor embedding pretty, like you want this one to be pretty high, and the one for the positive embedding like to be kind of close to your anchor image. Does that answer your question?
So just to add to that, like we also want to minimize the intra-class distance, and that's why we have 3. Like if you just have positive, negative, that we won't explicitly be modeling that part of the distance that we want to optimize.
Okay, thank you. That makes sense.
Cool. Okay, thank you. So the second approach will be something that you probably already know, since like this is the approach that we use in the start and notebook. So the first step will be to train a basic classification model, which is actually optimized using cross entropy. And the second one would be to reuse this trained model, perform face verification, and then like end this last by contrastive loss. So ideally, so this is a second example. So if you go with something like ArcFace, you actually need to include a new layer to your model, which is actually the one that will perform this margin product. So we've actually discussed this in yesterday's bootcamp. But the thing is, this will basically be a new layer to your model. And then given this new embedding from this output layer, you ideally use something like face loss, or you can still use cross entropy loss, depending on actually what you want to achieve. So what we actually want you to understand is like moving from your model, like your classification model for face recognition, you don't need to do like this much change your verification model to actually perform face verification. So like I said, you actually have to add this new layer. So that will replace your final classification layer in the face classifier, and you will then get your output from this final layer. So in this particular setup, you are not actually constrained to use the features from like the last layer of your CNN. Like you can still use the classification layer. The only thing is that you have a pretty high number of like a high dimensional output vector, which is basically 7,000 dimensional output vector, as opposed to something like 512 embeddings that you will actually have if you kind of reduce the number of output features that you want. So it is actually quite simple to build this verification network around your classification model. So you may want to make sure you have a pretty accurate classification model, so that when you come to this part, you just use a technique, namely transfer learning, instead of building and training your model from scratch. So ideally, this is a pretty hard homework. So you may see some differences from homework 1 part 2, which is basically that the first thing is like you have 2 tasks. And the second thing is the second task, like the second subtask, is pretty hard to solve. So we will be actually pretty impressed if you kind of come up with a pretty high score for verification. But like, if you have any doubts or any difficulty implementing your verification network, you can just try to come to office hours or ask your question on Piazza. So we now have a pretty short discussion around normalization. So we've actually seen batch normalization. You've also implemented this layer in your MyTorch module. So the only thing is, batch norm is actually used to apply normalization to a batch of input data. So there is a constraint that comes with this formulation, which is it really depends on the number of samples that you have in a batch. And this is actually an issue for your classification model, but like for any model that you kind of optimize or normalize using batch norm. Because let's take the example of like, you are pretty constrained, like you have this pretty low GPU memory available to you, and you can only fit 1 or 2 example for your batch. So the thing is, given this small number of samples in your batch, it will actually affect the way you compute those 2 terms, namely the mean and the standard deviation. So you actually want to have some flexibility on how to use your normalization across like something that is not a constraint to your model. So apart from batch norm, you can also use layer norm, which is basically somehow the same normalization, but this time we're applying this normalization to the channel instead of the number of samples that you have in a batch. So there is actually a key difference to applying normalization across channels, which is you can actually reuse the same mean and the same standard deviation for both test and training, which is basically impossible using batch norm, because like you have to kind of save and update the your mean and norm while training, and reuse those while doing inference. The second thing is you actually have a way of sharing these terms across your hidden unit. So it's still the same formulation, but here you're just applying the normalization across your hidden units, which gives you quite stable training as compared to batch norm. A disclaimer is, so during our ablations, we actually did something like changing layer norm for those architectures that actually use layer norm. So we actually changed this one to batch norm, and it seemed to perform better than the original ones, especially for this data set. So you may want to also try both and see if you observe the same things across your ablations. We also have something. Okay, a question.
Would you ever want to mix them, like do batch norm one layer and layer norm the next layer?
It's really it's really up to you. The only thing is, when you apply layer norm, So the way PyTorch implements layer norm is the channel will actually be considered as the last dimension. So you have to permute before you apply layer norm, and then permute it back to the original shape. But like you can just have like a network with both and see like how it performs. I don't know if I answered your question properly.
Yeah, sounds good. Thanks.
Oh, okay, good. So you also have something like group norm, which is more like a variant of layer norm. So instead of considering the whole channel, use a subset of this dimension to perform your normalization using the same rule as the original batch norm. And then you also have something like instance norm, which is I think this one will make more sense for people who are doing a project around image generation, or even people who will be working on GANs like for OMOC 5. So in this case, people usually consider this one as more like a contrast normalization actually. So it's really it considers only one instance, and the way it's actually perform this normalization layer is you actually need to remove some contrast for models such as stylization models. So I think we'll kind of discuss those such models in the upcoming lectures. But like it's also something that you may want to try for this one. But I guess for OMOC 2, using layer norm and batch norm will be quite enough for you to get to the high cutoff. So I guess Aditya, we will just like go through these steps, and then I will just walk you through the starter notebook.
Right. Thanks, Cedric. Is my screen visible?
I think it's loading.
Can you see it now?
Yeah.
Okay. So yeah, we're gonna quickly go over label smoothing and drop block. These are also two relevant tricks for this homework, but we want some time for questions about the starter notebook at the end. Right. I think we went over label smoothing in the class, but we'll just come over it here. So overfitting is something that we've talked about a lot, and we've talked about how we can address it. Augmentations is a big part of that, and like go to the bootcamp yesterday, I think we did augmentations in detail. But another problem when you have a lot of classes can be overconfidence, and label smoothing addresses that problem. So say we predict 0.9 consistently for one class, but our accuracy for that class is actually only 60%. Well, in that case, we would call it a poorly calibrated model. And a well-calibrated model would be that outputs a probability 0.9 for that class, and a majority of the time like outputs a high probability, and also gives a high accuracy. So that's what label smoothing addresses. And so for an example, without label smoothing, say we have three classes, and we get our logits Z as output of the ultimate layer of the neural network, of the penultimate layer. And our label vector is a one hot encoded Y. So the loss in case of the in case of, if you use a cross entropy loss, then the divergence will be 0 for all other components except the first one, the one that is the true label. And what we will try to do is we'll try to make the distribution of softmax of Z to be as close as the true distribution of Y as possible. And to do that, our model will then just try to increase A, which will naturally just always enforce B and C to decrease. And that may not always necessarily be the way to go about doing gradient descent. So what can happen is like, our network just becomes very confident about one class and like is uncertain about others. So one thing we can do to smoothen this whole process is label smoothing. And so this is the general equation of how you would formulate it. Y hot is our one hot encoded label. Alpha is a hyperparameter that you can tune, and K is the number of classes. So if you pass in like label smoothing alpha of 1, then you can see that the smooth ground truth labels will just be alpha by K, which is like 1 by K, or it will be uniform distribution. And if we use a alpha of 0.1 here, then we get the smooth ground truth labels as shown, YLS. So this is like better than what we saw earlier, better than just having 100, as now the logits will try to model this smooth YLS. And it sort of prevents our model from becoming overconfident about certain classes, and it aids gradient descent in this manner. Yeah, so I think it was also discussed in class, and I think that from our experiments and my experiments last semester, it was useful in increasing accuracy. So definitely experiment with it. Another useful tip here is about drop blocks. So dropouts work well with fully connected layers, but they haven't proven to be very useful for regularization for CNNs because of the spatial correlation between the activation outputs. So drop block is like a regularization technique that sort of addresses that and is more useful. So if you look at like this kind of activation map here, so you have an output of a CNN and then you apply an activation on top of it, and say that then you drop out, remove random features like how dropout does. But still, there will be some information about the pixel that you drop out. So say you drop out this pixel, there'll still be some information about this pixel that will be backpropagated back into the network by adjusting its neighboring pixels. And that's because of the spatial correlation and like the basic idea that, we're looking at window, it's a scanning approach. So our kernel will look at like 3x3 or 5x5 window at once. So dropping out randomly may not be as useful, like may not do what we wanted to do. So there's a new technique that's called drop block 2D that has proved to be useful. And it is a form of structured dropout that will drop structured regions from the activation maps instead of just dropping random pixels here and there. So the idea is that we will drop out these contiguous maps. So say like we have this activation map for a dog because we want to identify this dog. So if we want to use drop block, so say that we want to remove some like this contiguous region from the activation map, which could mean that we're removing information about the head of the dog, or yeah, the head is not there, but we want our network to still be robust enough to classify it. Or if it's this, then we could be removing a leg. So that information like that's masked will not be backpropagated. So how would you implement drop block? It's pretty simple. I think there are standard implementations in PyTorch as well, but it's like pretty simple to implement yourself as well. So you just pick a random pixel like you would do for dropout, and then you would just define a region around that pixel, and you would just decide to mask that off. Right. So that, yeah, again, like drop block proved to be useful in our ablations, and you should definitely experiment with it. So that's all about regularization. And yeah, I think we gave you pretty useful tips of like what will help you cross over the boundary. So keep these in mind. But to get close to the boundary, definitely go to the bootcamp. That has a lot of information for you to get there. And I think like Cedric has also emphasized this, and we also emphasize this in the bootcamp, like start early. Like your models in homework 2 part 2 are probably the largest models you will train in this course, like in terms of time taken as well, and like in terms of things you can experiment with. But yeah, we're here to help. And so let's go through the start. Cedric will go through the starter notebook. And yeah, if you have any questions about early cutoff, then or like, you know, implementing any of these, then we can address them here.
If you have any questions, feel free to ask them while we go through the starter notebook, either using the chat window or even like asking it by unmuting yourself. So I'll just go through the starter notebook. So basically you have mainly 3 different things to design or implement. So you first need to implement your data set. So these are actually the same thing as last homework. So you can just like, you know, pull this code from homework 1 part 2. So how you download the data set from Cargo, and how you kind of download everything into your Colab instance. Something I also wanted to mention is so we keep saying that this homework is hard. I think like it's just something that is kind of a way for us to say that it would take time for you to understand and even to get your model across any of these cutoffs. So please don't train your model for only 10 epochs and then like start like worrying about like your model not crossing any of these cutoffs. Like it definitely takes more than 10 epochs to even cross the medium cutoff. So the first thing will be to implement your data sets, which is basically pretty straightforward for this homework, since we're using this package from PyTorch, which is image folder. So we're using this one because when we use VGG face, we actually have all the given faces into their respective folders. So using these methods from PyTorch, you actually get to map any image in this folder to the name. I think Aditya, you want to say something?
Yeah, sorry, this is slightly unrelated, but I just wanted to mention it before I forget. We don't have a parameter limit for this homework. Earlier we did. So like that should immediately hint you towards trying ensembles. Also, I don't remember who asked this earlier, but I think someone asked if we have one-to-one mapping. I just went back and checked, and I'm sorry, it's not a one-to-one mapping. Yeah, that's like it's a one-to-many mapping essentially. So just wanted to clarify that and confirm it. All right, cool. Sorry, Cedric.
Yeah, that was much useful. So the first thing is you can actually see that you just go to the next cell. You actually have this number of input images. So when you divide it by this number, you just like see that you only have 20 images per class. And we've said that you have to train a deep learning model. So 20 images are kind of not sufficient for you to get an accurate model. So the remedy for you to actually get to let's say the medium cutoff is data augmentation. So data augmentation was discussed in yesterday's bootcamp, like it is basically a technique to create new samples without actually having them like as your normal images. So you can actually achieve this using Python transforms library. So you have different type of transformation that you can use for this homework, but like keep in mind that you're dealing with faces. So there are some transformation, let's say something like vertical flip, that may not be a good idea to try for this homework, since like you actually have the faces like in the same direction. So this one will be pretty straightforward. It's just like you actually have to kind of select the augmentation that you want to try for this particular training pipeline. It's so usually it doesn't make sense to kind of like perform data augmentation on the validation set, but there is a technique called test time augmentation, which sometimes gives some performance boost. So you may want to try that one, but it's definitely not something that is required for your model to reach the cutoffs. So you will actually have different data set for classification and tests, given that for the test set, you don't have the labels. You can still implement this one using the same logic as mock 1 part 2. So then comes network. So you can actually read all the comments that we actually provided in the starter notebook. The only thing is for the very low cutoff, like we also provided some guidance to what should be a very basic network that you need to implement to kind of get your early submission. You also need to consider that we also provided this implementation of how you kind of return the features or return the output of your layer, which is essentially useful for verification tests. But like it really depends on how you decide to implement your verification network. If you go with something like ArcFace, we have to implement the margin product yourself. So this is also one reason why we say this homework may be quite challenging, because any given module that you want to use for your homework, especially those that are part of your network, should be implemented from scratch and trained from scratch. And let's go to, yeah, so this is also the same logic. You have to define the loss function, and optionally, you can also define a scheduler. This may be quite useful for this homework as well, but it's definitely something that you can actually skip and train your model without scheduler. So how you train your model, we also provided this training logic as well as the validation logic. So what will be quite different from homework 1 will be the verification task actually. So so this is how you generate your CSV file. So we've discussed this in the previous slides. So you actually have a set of known faces and a set of unknown faces. So like Aditya mentioned earlier, it is more like one-to-many mapping that you need to solve in this problem compared to the original one-to-one verification task that we used to have for homework 2. So we actually provided this verification evaluation method. So feel free to go through it, and if you have any doubts, you can also reach out to any of the TAs. So yes, to kind of get everything up for these tasks, you basically need your network, and the very basic network will just be a stack of convolution layers as well as normalization and activation layers, and nothing pretty difficult. So unless you have any question about the starter notebook, I think we can call it a day.
One quick question on that. I tried just running the current verification code without changing anything, and it wasn't able to be submitted to Kaggle. Is there stuff we have to do to change things a bit before it can be submitted?
Yes, so I think this might be the reason why you actually, because for the set you actually have 1,000 images, but like in the dev set you only have 200 or 800 samples. So you need to set this mode to test so that it skips this if condition. Then it will just like generate these IDs, and then you would just have to use them to generate your submission file. So I guess like for the test set, you actually need to change
changing from valid
yeah,
test
or like
should do it.
Any string will work though.
Okay, thanks.
Yeah. Any other questions? Otherwise, like we actually encourage you to go and watch the bootcamp, because like we have many tips that we gave yesterday, as well as like what we found quite useful to try during our ablation. So feel free to go and watch this recording and come up with your questions on Piazza or like during office hours if you want. So I think we're good to go. So thanks guys for joining us today, and I think we just call it a day.
Yep. Thanks everyone. Best of luck for homework too. See you around.